So I believe we are live at this point. And so welcome everybody to the ICSI 2020 Awards ceremony. I'm Alex Orso, the awards chair, and I really wish we were doing this from South Korea, but unfortunately we are not, so I thought at least to arrange a suitable background. So the goal of this session is to basically celebrate several important awards. I'm just gonna quickly mention them, and then we're gonna start presenting them, and then there's going to be time also for questions. And the awards are the ACM Student Research Competition Award. Then we're going to have some awards from one of our platinum sponsors. Then we're going to present the ICSI Most Influential Paper Award, the Harlan Mills Award, and last but not least, the ACM Sixth Outstanding Research Award. And I'd like to remind the audience that you can ask questions to the presenters, and to do that you have to go on a Clouder, or you're probably already on Clouder, and on the lower left corner you'll be able to type your questions, and then the chair will be able to read your questions and ask the presenters. So we're going to start without any further ado with the ACM Student Research Competition, and this award will be presented by Andy Bagel.
Thank you very much. Let's go and share here. So hi, my name is Andrew Bagel. I'm from Microsoft Research, and my co-chair, Junbom Yu, and I ran the ACM Student Research Competition this year, which also happens to be sponsored by Microsoft Research. So the Student Research Competition is a contest for undergraduates and graduate students to show off their research to the software engineering community. It consists of 3 rounds. There's a round of abstracts, which are 4-page abstracts. We had 30 submissions there. If the abstract is good enough, it gets accepted into the conference, at which point the students get to present a poster. And so we had 3 rounds of poster sessions across the different time bands of ICSI with 18 participants, and fortunately 6 participants in every time band. And then the top 5 graduate and top 5 undergraduate participants were accepted into the presentation round, which just happened yesterday, across the 3 time bands, in which we had actually 9 participants because there were only 4 undergraduate participants in the contest. This competition results in a set of prizes. First place receives $500 and an invitation to participate in the ACM Grand Finals in April. Second and third place receive $300 and $200 respectively. And all participants, when you come to the conference, get a travel stipend of $500. Maybe not so much this year. And so I want to first thank our first round of reviewers. We had 25 reviewers from across the world helping us read those abstracts to figure out which of the participants we should accept into the contest. And then we employed 32 judges, and this was a heroic effort by a huge number of people to review the posters and presentations of all the students. So thank you from the bottom of my heart, all of you, for showing up every day for the hour and then submitting your scores to us in a very timely manner. Without further ado, I'm going to announce who the student winners are. So first, for the undergraduates, in second place was Shashij Gupta from IIT Bombay, talking about machine translation testing by pathological invariance. In third place was Ananga Tapalia from Innopolis University, evaluation of brain activity while pair programming. And first place is Vikram Subramanian from the University of Waterloo, who spoke about an empirical study of first-time open source contributors on GitHub. So congratulations to the undergraduate winners. And now we move on to the graduate student winners. I'll read these backwards. In third place, we have Tegan Brennan from UC Santa Barbara, who spoke about detection and mitigation of JIT-induced side channels. In second place is Rangit Pan from Iowa State University. Does fixing bugs increase robustness in deep learning? And finally, in first place was Alberto Martin Lopez from the Universidad de Sevilla, who spoke about an automated analysis of interparameter dependencies in web APIs. So I'd like to congratulate all of the winners, and they will be receiving certificates signed by the co-chairs of the ACM SRC, as well as the general chairs of the conference. That'll come in the mail at some point. And the ACM will be contacting you to find you to give you your monetary awards. So thanks everybody for participating, and let's go back to Alex.
Thank you, Andrew, and congratulations to all the winners for the interesting work. So before we move to the next award, this year we offered our platinum sponsors the opportunity to say a few words to the attendants. And we're very grateful to Facebook for its generous support for the conference. So we are now going to play a video that they provided. So Iftikhar, if you want to start the video.
For me, it's about the early mornings and the late nights.
It's about finding time for myself and time for others.
It's about the quiet moments where I gather my thoughts. It's about the loud places where these thoughts are given life.
It's about connecting and perfecting.
And creating again.
It's about the anticipated.
And the unexpected.
It's about sharing and encouraging.
It's about bringing the world closer together.
It's about crafting a culture for everyone so that all voices are heard.
It's about reaching your goals, but never settling.
For me, it's about.
Thank you, Iftikhar, and thanks again to Facebook for the support. So now we're gonna talk about. I'm gonna present the ICSI Most Influential Paper Award from ICSI 2010, and the award will be presented by Prem Devambu. That was one of the two co-chairs, together with Sebastian Uchitel, of ICSI 2010. So Prem, you have the stage.
Thank you, Alex. So the committee was formed by Sebastian Uchitel and myself. We were the program chairs of ICSI 2010. We were very concerned to have a committee that balanced younger people, people who have been publishing a lot more recently and would have well positioned to give us a view on the papers that they considered influential in their careers. So the committee members, besides Sebastian and me, consist of Federica Saro, professor of computer science at UCL, Alessandra Gorla, professor of computer science at IMDEA in Spain, and Professor Lin Tan from the Purdue University in the US. So together with them and the general chair of ICSI 2010, we looked at the papers that were published in ICSI 2010. We first started off by filtering the papers that were very heavily cited, and from that point onwards, we looked carefully through the rest of the papers. We picked the top most cited papers and looked through them, and selected a paper that we felt was the most influential. The paper that we selected was not just simply cited in our community. It received citations, non-self citations from conferences like NeurIPS, HCI, VLDB, CCS, ICML, VLDB. Many other conferences in other areas were cited this paper. So it was not just influential within the software engineering community, it was broadly influential and continues to be that way. So the paper that was selected, I'm happy to report, was entitled Oracle Guided Component-Based Program Synthesis. The authors are Susmit Jha, Sumit Gulwani, Sanjit Seshaya, and Ashish Tiwari. So I'm very happy to introduce that paper. and congratulate the authors for winning this award, which is very prestigious and reflective of long-term durable influence in the community. Over to you, or Alex.
Well, I think at this point that we can start with the presentation. So if the or if you're just gonna share the video for the presentation.
Thanks, Prem. Thanks, Alex. I'm going to share my video now. Let me know if you can see my screen.
Yes, we can see.
Hi, I'm Sanjit Seshia, a professor at UC Berkeley. At the outset, I would like to thank the award committee for this honor and the broader community for your interest in and the follow-up research to our work that has enhanced its impact. In this presentation, we will begin by first looking back at our work, then at the results obtained in the decades since, and finally to the exciting future directions that remain to be explored. So looking back, our ICSI-10 paper made three major contributions: Oracle-guided learning, component-based synthesis, and certain novel applications of synthesis. It was also one of the first works to explore the connections between the new wave of program synthesis and the field of machine learning. So let's look at these three contributions in more depth. The idea of Oracle-guided learning in this paper was to formulate synthesis as a dialogue between a learner and oracles, where the oracles can answer two types of queries: an input-output query that, given an input, produces the corresponding output, and a distinguishing input query that produces inputs that differentiate a candidate program from other consistent programs. The paper also made a link to machine learning, more specifically to machine teaching. The second contribution was to think of synthesis as assembling programs from components. For loop-free programs, the components were operators, and there was an efficient encoding to bit vector SMT solving. The third contribution was to introduce new applications of synthesis, such as synthesizing bit hacking tricks and simpler versions of obfuscated malware. In fact, the idea to use a distinguishing input query arose because we realized that standard verification queries were too expensive for some of these applications. So how did these ideas come together? From my own personal perspective, the journey began more than 20 years ago when, as a fresh PhD student at CMU, I was interested in both machine learning and formal methods. And while my PhD thesis on the Euclid SMT solver and verifier explored this a little bit, I started pursuing this connection between the two fields in earnest when I joined the faculty at UC Berkeley, and it was the theme of my NSF career project. Concurrently, I started working on program synthesis with Raz Bodik, then a colleague at Berkeley, and Armando Sola Lezama, who was then a student, and we developed the technique now called counterexample guided inductive synthesis, or CGIS. Around the same time, Sushmit Jha started his PhD at Berkeley under my supervision, and we worked on several topics, including SMT solving for bit vector arithmetic, program synthesis, and in collaboration with Somesh Jha on malware detection. It was in this context that Sushmit started a summer internship at SRI in 2009, seeking to work on exist-for-all SMT solving and on synthesis. It turned out to be a fruitful summer collaboration that led to the writing of our ICSI-10 paper. So now let me look at the decades since we wrote that paper. And I would like to point out that one of the most exciting trends has been the confluence of formal methods, program synthesis, and machine learning. From my personal viewpoint in 2009, I had two epiphanies. First, I realized that many tasks in formal methods, including specification and verification by, for example, proofs by induction, compositional reasoning, abstraction, and so on, all reduce to synthesis problems. Second, I realized that the ICSI-10 work, CGIS, and other projects were all instances of a more general approach to synthesis, one that combines inductive learning, deductive reasoning, and a hypothesis about the structure of the artifact being synthesized, which we now term as syntax guidance. We term this approach as SciDuction, or more concisely as SID, and we wrote a string of papers on this, starting in 2011, 2012 with a DAC 2012 paper and Sushmit's thesis, and then following up with a more detailed article in the Proceedings of IEEE. In the years since, especially in projects such as Escape, TerraSwarm, and VCal, these ideas have been demonstrated in a range of application domains, including software and hardware verification, education, cyber-physical systems, robotics, including human robot systems, and machine learning. This approach to formal verification is now also implemented in a new toolkit called Euclid 5, which is an effort that has been co-led by my former postdoc, Pramod Subramanian. In particular, we have been interested in understanding the theoretical connections between machine learning and program synthesis. A key result appeared in our 2017 Acta Informatica paper, which has three major results. First, it establishes the theoretical framework of Oracle-guided inductive synthesis, of which CGIS and our ICSI-10 work are both special cases. In contrast with models that are commonly used in the machine learning literature, such as active learning or query-based learning, in Oracle-guided synthesis, one is allowed to design both the learner and the Oracle given and so-called Oracle interface, which defines the communication between the two. Our second result uses this framework to characterize the relative power of different variants of the CGIS approach. The third result shows how the notion of teaching dimension introduced machine learning theory can help characterize the complexity of certain Oracle-guided synthesis methods. Taken together, these form an initial theoretical framework for formal inductive synthesis, which now other researchers are starting to build upon. To end the segment, we consider the influence of our paper on the work of other groups that cite it. These fall into two categories: those that mainly use the Oracle-guided learning idea, and those that follow up on our component-based synthesis approach. As you can see, they span a variety of use cases, not only program synthesis, but also software testing, hardware security and verification, program repair, and super optimization. In the next segment, Sushmit will present his perspective.
Hello, everyone. Let me begin by introducing myself. I am Sushmit Shah. I'm a principal scientist at SRI International, where I lead the research on trust, resilience, and interpretability of AI. We're looking at how to extend and apply Oracle-guided synthesis to make deep learning models more transparent and trustworthy. This work is currently supported by different projects from various US government agencies. In particular, I lead the DAPPER project at SRI on assured autonomy and synthesis of intent-defined adaptive software. I'm also the PI for the SRI team on IAPA project on reverse engineering deep learning models for detecting Trojans in AI. I'm one of the PIs on Army Research Lab's Collaborative Research Alliance on the design and monitoring of Internet of Battlefield things, and NSF projects on self-improving CPS systems and duality-based algorithm synthesis. Now, to give you some context on our ICSI 2010 paper, as many of you know, program synthesis has been an active area of research for at least half a century. In fact, one of my colleagues at SRI, Richard Waldinger, had a paper in 1971 where he looked at automatically synthesizing programs from logical specifications. The examples in this paper included programs for sorting, reversing lists, and computing Fibonacci numbers, which you will find in papers even today. His line of work belongs to the class of purely deductive program synthesis techniques. There's also been a significant amount of work on inductive program synthesis. One of the earliest work was by Daniel Halbert, who wrote his PhD thesis at UC Berkeley on programming by example in 1984. And if you look in his thesis, he talks about spreadsheets, control structures, and even robotics. And these remain hot application topics of interest even today. More recently, a major revival in interest in program synthesis came with Armando's PhD work on counterexample guided inductive synthesis. In 2009 and 2010, when we were working on ICSI 2010 paper, I was a graduate student at Berkeley and a summer intern at SRI working with Ashish, who was at SRI International then. This gave me exposure to both purely deductive approaches to program synthesis originated at SRI and inductive program synthesis being pursued at Berkeley. This led to a natural fusion of ideas, and we came up with a new paradigm that combines the strength of both approaches. We called it structurally constrained induction and deduction, eka, sideduction, The key idea is to allow the specification in the free form of an oracle, instead of having just logical specifications or examples, both of which are often difficult to provide. This idea of oracle-guided synthesis was a core contribution of my PhD thesis, and we applied it beyond program synthesis to other applications such as reverse engineering and synthesis of continuous and hybrid controllers. Our ICSE 2010 paper is an instance of this approach applied to program synthesis. My co-authors will talk more about the oracle-guided learning framework, how it originated from the need for relaxed specifications, and its specialization for program synthesis. I will highlight some of the milestones from this journey over the last 10 years in bringing automated synthesis to real world beyond traditional applications of macro synthesis, spreadsheet manipulation, and code optimization. Since I have only 7-8 minutes, I will not go in detail here, and if you find it interesting, you can look up the references or get in touch with me directly. The first milestone was application of synthesis to hardware design at Intel, where we demonstrated its utility in automated synthesis of network on chip for the Intel 14 nanometer SoCs. We then showed how to use oracle-guided synthesis to configure platforms for improving the user experience, power, and security profile. The next milestone was in context of autonomy, when I was at UTRC, which is a research lab of Raytheon Technologies. Here we applied synthesis for design of collaborative human-machine teams operating in uncertain environments. More recently at SRI, we showed the value of synthesis in the context of systems. Consider a scenario with multiple aircrafts from different manufacturers and even different nations, similarly different land and sea units, all operating together in a mission for the first time, without any common message formats or protocols to talk to each other. The question here is, how do we automatically enable these agents to communicate? How do we generate those message formats? How do we synthesize those protocols on the fly in a rapidly evolving environment? Finally, the last highlight is our application of oracle-guided synthesis to analysis of deep learning models, which we have been pursuing for the last 4 years. We have 2 directions in this thrust. The first is to reverse engineer and validate deep neural networks. And the second thrust is to characterize uncertainty in prediction of machine learning models and to make them more robust to adversarial attacks. If you're interested and want to join us on this journey, please send me an email. We are hiring. Now, looking back, there's been some very interesting papers on program synthesis over the last 5 years that cite and build on our work. In particular, Sumit's group at University of Texas at San Antonio has made some remarkable progress on nanoscale computing using program synthesis. Another very interesting extension has been the work by Armando and Josh at MIT in using program synthesis for unsupervised learning. In the end, I would like to acknowledge all the institutions and funding agencies which have supported my work over the last 10 years. I thank the ICSE 2020 Most Influential Paper Award Committee for recognizing this work. This is extremely encouraging to me as a researcher. Reminiscent of the story of an elephant and 6 blind men, in research, interesting ideas often tend to have multiple facets. So we'll next hear from Sanjit, Sumit, and Ashish on their perspectives and follow-up work on this topic. Thank you.
Hello, everyone. This paper is an important point on the journey of bringing program synthesis to the masses, to end users, data scientists, and developers. I will describe this journey from the lens of achieving minimalism in a specification burden on the customer. The journey started with a desire to synthesize complicated algorithms with tricky, non-intuitive components from logical specifications. For instance, how do you multiply 2 2x2 matrices using 7 multiplications instead of 8? That's a question I asked my instructor in an introductory programming course when he mentioned this fact. His response was, this premium material is only meant for an elite class of students who qualify to take an advanced algorithms course. I reapplied to college and wasted 1 year of my life to enter that elite class. That scar remained until the first synthesis paper that I wrote, which described a technology to automatically synthesize this algorithm and its several variants. Coincidentally, this popular 2010 paper recently also won the most influential paper award. So much for vindictive inspiration. This paper made us realize that logical aspects are too complicated. We wondered, what if the user expresses intent using examples? But examples are extremely ambiguous. That's where this ICSI paper shows that the user can be guided to provide the right set of examples to converge to the intended algorithm. My manager wasn't impressed and asked, have you been able to synthesize a new algorithm? In fact, that's the most common question I got asked. I quickly realized I can't make the machine compete with Nuth. So instead, I found customers who would be grateful with the loop-free programs that machine can synthesize for them from examples. But there was a big challenge. To earn the customer's trust, you need to make this thing work with one example for common cases. For instance, suppose you have a bunch of strings in the form first name dot last name at domain, and you want to extract the last name. 99% of spreadsheet users do not know programming and would struggle with such a task, but can easily specify what they want using examples. The Excel team told me, Sumit, this is cool, but you can't ship this unless you make it work with one example in most common cases. So that's what I did. And the resulting Flashfill feature now is one of the most popular features in Excel and has around 1 million invocations each week. Flashfill can automate a wide variety of string transformations, but there are many tasks that it cannot do, such as number or date transformations. The user experience, however, is so inviting that people invariably want to give it a try, even on tasks that it was never meant for, and then talk about it when it does not work. There was a recent tweet with tens of thousands of reshares. AI is going to take over the world. Look what Excel auto-populated for me today. When they converted DEC to December, Flashfill auto-completed JAN to Janember. Some people even came to the rescue of the Flashfill feature, arguing that this is how we should have named months in the first place. I recently came across this shipping label where someone even decided to incorporate Flashfill as part of their process automation. The best thing about such a customer feedback is that now you know what to prioritize. And while we can now handle such tasks, there is pretty much no limit to how intelligent can the synthesizer be for such map transformations. How much further can we push on this journey of reducing spec from one example? Well, how about 0 examples? That's what one of the product teams demanded when we approached them with the idea to help data scientists extract clean tabular data from semi-structured documents like web pages, PDF, text files, just by giving a few examples of various fields. They said, Sumit, we don't have time to build a UI for the user to provide examples. Can you make it work with 0 examples? Initially, I thought they were crazy, but then we realized it made sense. We call it predictive synthesis, wherein intended programs are just synthesized from just the input. You can liken them to unsupervised learning in the machine learning world. The data connector that ships in Power BI allows the user to simply point to a web page, and a parsing program for extracting tables is synthesized. If the user is not happy with the table, they can then leverage the by example capability. Is there anything else on this journey? Well, what about the user not even expressing their desire explicitly, and we serving them with what they need, like the Clippy, but a more intelligent version this time around? Consider the task of making the red-green edits in this code base, where the goal is to lift the model variable from being part of an argument list to an invocation expression. The new IntelliCode suggestions feature that is now shipping inside Visual Studio can learn the user's intent from a few example edits as hidden in their natural but noisy workflows, and is able to automatically suggest other related edits. We call it modeless synthesis. And the technical problem that it yields is that of guessing what the examples of any repetitive pattern even are in the underlying trace of keystrokes. Most of the code that developers write is boilerplate code, plumbing code, and there is very little algorithmic creativity involved. There is an opportunity to improve the developer productivity by almost 10 to 100x. If you look at the history, we went from punched cards and assembly language to high-level languages and beautiful code editors. The next evolution will take programming closer to human conversation, wherein it will be multimodal, involving use of examples and natural language to express intent. What I showed you was a start, but very significant because of real-world adoption. Customers are now asking for more, and this is where we need more powerful techniques. A big technical opportunity is combining logical reasoning techniques, which can precisely model program semantics, with machine learning techniques, which can model the bias in real world and user's intent. However, there will always be scenarios that will not work in one shot. We need to fall back to interaction when faced with complicated or bigger scenarios. This is where we want to find even more inspiration from this very ICSI paper to make the computer act as a peer programmer or an observational assistant. Thank you, folks, for being so ahead of us in recognizing the significance of this work.
Hello. First and foremost, I hope you and your family and your loved ones are safe and healthy. Next, thank you. Thank you for recognizing this work. Today, I'll be sharing my views on the impact of this ICSI 2010 paper. Let's start off by talking about precision versus ambiguity. In computer science and software engineering, we value precision. Programming languages should have well-defined semantics. And what this precision allows us to do is to write good software. We can write programs that can be run, they can be tested, verified, and shared, all because they have unambiguous meaning. In real life, on the other hand, we value ambiguity a lot. If you think of all famous quotes or philosophies of the world, they all have multiple interpretations. People provide different meanings to the same thing, and this multiple interpretations of the same thing provides new ways of looking at things, and it's a virtue. In scientific papers, on the one hand, we need research results which have to be precise. But on the other hand, scientific papers are also assigned a value based on subjective interpretation of what is the meaning of those results, what is the impact of those results, what do the results really mean. And my claim is that these multiple interpretations, the more there are, the better the paper. So, what about the multiple interpretations for Oracle-guided component-based synthesis? At the highest level, you can latch on to one of three things from the paper: the idea of input-output examples, the idea of Oracle-guided synthesis, or the idea of component-based synthesis. Input-output examples, there are multiple flavors. You have both the input and the output specified, just the input or just the input range. And depending on these flavors, you can combine them in various ways and get very interesting program synthesis problems which have a lot of different applications. I'll highlight the case in which the input-output examples are actually hidden, called modeless synthesis, in which you have to actually extract out the input-output examples before you can do synthesis, or performing synthesis with only additional inputs and no explicit input-output examples, which is called predictive synthesis. Beyond program synthesis, input-output examples have been used in learning from demonstrations in robotics, in machine teaching, reinforcement learning, and many other places. And in each of these applications, they have their own interpretation of what is an input-output example. And in each one, we are learning from well-chosen input-output examples. Again, picking the right input-output examples was one of the things that we did in this paper. Let's come to the Oracle. Oracle is a thing that's providing the input-output examples. Who is the Oracle? One way of looking at the work is that the end user is the Oracle. The user is providing the input-output examples and trying to synthesize code. Another view is the complex specification is the Oracle that provides the input-output examples, which are in turn used to actually perform synthesis, because directly synthesizing from specification was not feasible. Another view of the Oracle is that the Oracle is a teacher, or the Oracle is really a student who asks the question and teacher who provides the output, and so on. Finally, let's come to component-based synthesis. Component-based synthesis is the idea of doing program synthesis by composing given components Now, what is a component? Again, one can imagine that a program with holes in it define components, so that you actually write a whole program by instantiating these components and composing them. Or components are just domain-specific languages. Or components are domain-specific languages with some kinds of composition constraints. And all these are valid interpretations and valuable interpretations. Components allow us to perform synthesis at an abstract level. So what this means is that a very simple program over complex components could be the same as a very complex program over very simple components. Also, components allow us to perform different, they enable different applications. For example, if the components are basic ruler compass operations, then synthesis will produce geometric constructions. If the components describe encryption, decryption primitives, then synthesis can be used to generate secure multi-party computation protocols and security protocols. So finally, I'd like to conclude by saying that multiple interpretations create value in an idea. And it's not the authors that impart all these different interpretations. It's actually the research community, the people who read the paper, interpret the paper in their own way, impart meaning to it. So really the recognition of this paper is a recognition of the people that gave meaning to it, which is you. So thank you.
In conclusion, we see many exciting future directions for research on Oracle-guided synthesis, including on developing its theory even further and on exploring new applications in defining the future of programming, personalized education, programming swarms of IoT and cyber-physical systems, safe human-robot collaboration, and on trustworthy and verified AI. Thank you for your attention.
Well, thank you for the presentation. And Prem?
I'm here.
All right. So now you can handle the questions.
Yes, there was one question on the chat. Sumit already answered it, but I'll let you answer it on the air. Does flash fill show the generated function, or does it just apply it? And if it showed it, I guess I'll add my own question. If it showed it, would it be easy for people to understand?
Sumit,
you might be muted.
Okay, yeah. So the version of FlashFill that we shipped in 2012, unfortunately, hasn't been refreshed since then. So no, we do not see programs in Excel. But having said that,
I'm sorry, I lost the voice again.
This is what will help create the trust with the user. And there is also a possibility that we may not be able to generate 100% what the user wants, but we can give them a start, and then they can take that readable program and modify it, update it, and edit it in their workflows.
So if you have other questions, please feel free to put them in the chat. Does anybody else in the Zoom group want to ask a question?
I see a question about Rubinstein's requirement apprentices, and that's a very good observation. That was one of the first program synthesis work, and I think there they discuss not just synthesis of programs, but even requirements. One key difference that we observe between that line of work and what is currently pursued for program synthesis would be those were purely deductive approaches. And now there's a heavy emphasis on learning from examples along with doing deduction from specifications.
Yeah, indeed, actually, I think the use of techniques from inductive program synthesis, specifically for synthesizing specifications and requirements, that I think has really exploded over the last decade. And so, and I think it shares this feature of being small, right? So these are, you can think of requirements or specifications as small programs that one can convey with the multimodal inputs, including examples and other kinds of inputs.
Right. And I think the key observation in Howard's work was that if you think about program, and then he has a abstraction layer of implementation and requirements, they are essentially the same entity being described at different levels of abstraction. So you could synthesize each one of them. The difference between requirements and programs is only about how much details you provide. So obviously, everything that is currently being done for program synthesis would be applicable for those problems as well. I think there's another question here about readable program synthesis. Unfortunately, oh, this is Sumit's answer. Okay. I don't see any other questions on the chat.
I don't either. Any other questions? I guess I can turn it back to you, Alex.
Hey, so let's thank again the speaker and congratulations again. This MIP awards and in general impact awards are very prestigious, and also because they indicate kind of lasting impact and lasting contribution. So congrats for the great work. And at this point we will move to the next presentations, the next part of the ceremony, which is the Harlan Mills Award. And in this case, the award is going to be presented by one of our general chairs, Greg Rothermel. So Greg, you can take it from here.
Thanks, Alex. Yeah, I'm serving now not as one of the general co-chairs, but as the chair of the selection committee for the Harlan D. Mills Award. Let me just tell you a little bit about that. The Harlan D. Mills Award, recognizes researchers and practitioners who have demonstrated long-standing, sustained, and impactful contributions to software engineering practice and research through the development and application of sound theory. Everyone's open to nominate people for this award annually. This is the 2020 award happening now. Nominations for the 2021 award are being taken, and that process is open until October 1st. Just Google Harlan Mills Award and go to the IEEE pages, and you'll find them. Yes, okay. So the process for this is, we take that nomination, and then there's a selection committee. This year it was Matt Dwyer, Mark Harmon, and Gail Murphy. Thank you folks for taking part. And the committee reviewed the nominations and ended up selecting the 2020 nominee, Nachi Nagappan. The citation for his work is for outstanding contributions to empirical software engineering and data-driven software development. Just a few words about Nachi. Nachi's a partner researcher at Microsoft Research. He's part of the software analysis and intelligence team there. His research focuses on data analytics and machine learning in the realms of empirical software engineering, software reliability, software metrics, and developer productivity. He's published over 100 journal and conference papers, several with Best Paper Awards or Influential Paper Awards. Also, though, and this is important for the Harlan D. Mills Award, his work has seen a great deal of industrial impact in terms of tools to help developers and customers that have been released and that are still in use. So with that, I'll turn the floor over to Nachi. Congratulations, Nachi.
Thank you. Thank you very much, Greg. So actually, thank you very much, Greg. It's actually my great honor and pleasure to actually accept this award. I'm actually very flattered to think that the committee thought I was worthy of this award. Thank you to everyone in the broader community as well. Greg gave a professional overview. I wanted to actually give a little bit of a personal overview. I graduated from NCSU, where I was advised by Laurie Williams. I had an amazing time working with Laurie for several years. I read a lot of Franco-Belgian comics, and that's a great way to start a conversation. I attend comic conventions.
and I'm into railroad modeling, G and HO scale. And my full name is Nachi Nagappan, but I always go by Nachi. And this is actually how our group typically looks. I mean, we have a tradition going back 15 years. Every summer, we actually take pictures with our visitors, interns in front of the Microsoft sign. But because of COVID this year, actually, I mean, first of all, I couldn't give this talk in person, and all the visitors, interns to our group have been remote. So this is how actually our group looks like right now. Everybody's calling in weekly to keep in touch with each other. And more so, I wanted to actually give a shout out to some of our interns and visitors this year. We have an amazing bunch of interns and visitors this year. I especially want to call out Courtney Miller and Yu Huang. Courtney Miller is a rising fourth year undergrad at New College in Florida, and she's actually applying to grad school. So if you're looking for PhD students, she's interned in CMU before and with us, and you should definitely reach out to her. Yu Huang is a student of Wes Weimer at UMich Ann Arbor, and she's actually graduating with her PhD. So she's applying for faculty positions. So you should definitely reach out to you or Wes or myself. We are happy to make an introduction. And I wanted to actually take a high-level overview of some of the work we've done, and I wanted to move forward partly in terms of a technical talk, but also acknowledging all the people who've made significant contributions to software engineering and to some of this work. So software analytics has actually been there for a long time. There are various questions that people have asked, like, what metrics are the best predictors of failures? And what is the direct relationship between test coverage and quality? How much should we increase coverage? Can we actually predict if strong code ownership is good or bad for quality? What is the economic analysis of doing test-driven development? Various aspects of empirical software engineering and analytics which require us to analyze data that actually comes out of software systems. And towards that end, I mean, a very broad overview of the history of software analytics. I mean, probably the first reference we could find was Fumio Akiyama, kind of quantified what is known as the size law, and McCabe actually defined his cyclomatic complexity or code complexity metric. And Barry Baim at that time started working on software estimation. And then in the 80s, Vic Basili and Dieter Rombach started working on empirical and experimental software engineering in University of Maryland and at Kaiserslautern. And Audris Marcus, Elaine Weyuker, Tom Ostrand, and many others at Bell Labs started working on analyzing the PHY-ESS switch, leading the foundations of such software analytics. On a more recent note, Ahmad Hassan actually co-started the Mining Software Repositories Conference in 2004. And along with Tim Menzies at the same time, who started the Promise Conference, building shareable data and shareable models and building a community in that regard. And at the same time, I actually started at Microsoft Research, working on empirical software engineering. And Ahmad Hassan actually founded the SAIL group in Canada at Queen's University. And a more significant event was DJ Patil and Jeff Hammerbacher coined the term data scientist, which is now extremely popular in professional circles to define their jobs at LinkedIn and Facebook, starting a wave of data scientist positions who are actually analyzing data from software systems to make improvements not just to the software system, but also to the overall environment. Related to this, Dongmei Zhang founded the analytics group in Microsoft Research Asia, also focusing on improving developer productivity and software analytics. So this kind of led into the NSF workshop on the future of SE in 2010, which was very well attended. So there's been a broad scale community effort in this regard. And even there's been a fair amount of mainstream press about the impact of software analytics and empirical software engineering. For example, articles in the Forbes magazine or other places which talk about how functional languages actually have the best scores for software quality, how free apps with ads might be killing the phone's battery, and the presence of gender bias in the open source community. All these have all been different variants or variations of the empirical software engineering work and the analytics work that's happened in SE. And the recent boom on the growth of data scientists and data science positions is something of great happiness to the software engineering community, because this has actually advanced the state of the art by having non-researchers explore a fair number of these questions that they face in their day-to-day jobs. And even at a corporate level, several companies have started actually having data-driven or data-oriented decision-making as part of their focus. Like, for example, one of the quotes directly pulled out was, being customer-focused, customer-obsessed, data-driven, speed-oriented, and quality-focused. In a similar regard, having the resources available in terms of data and applied science to focus on measurable outcomes for our products are now mandated as part of charters and companies at a very senior level. So while setting up the context, it's always important to look back. And I would actually fail to, I shouldn't fail to acknowledge the contributions others have made. So one of the things I take great pride in is I have never actually written a paper on my own. I've never written a solo authored paper. Every paper I've written has actually been with somebody else in academia or in industry. And I think this is the right time for me to also acknowledge a lot of their contributions. So sequentially, I want to actually call out a lot of people who've actually made significant contributions to software analytics and empirical software engineering. To begin with, Tom Ball. So Dr. Ball actually so I also want to use this as an opportunity to look back at prior work and acknowledge folks. So Tom Ball and I had the opportunity to work on 3 different papers, 2 of which I want to call out. One is actually the use of static analysis tools as early indicators of pre-release defects. So the goal was static analysis find a particular category of defects. The goal is to actually look for types of defects that are not found by static analysis tools, so that we use static analysis warnings as early indicators to see whether the code is of acceptable quality. The second is the use of relative code churn measures to predict system defect density. This is so as to predict artificially inflating any prediction we see, so that we can have a cross-check mechanism. The last came about from a conversation with Tony Hay. So Sir Tony Hay talked about his philosophy on the use of assertions. But upon digging up further, we found no empirical evidence of the relationship between software assertions and code quality. So we actually undertook a fairly large-scale study on several code bases at Microsoft, where we actually found a clear relationship between the use of assertions and quality. And this study was actually part of the foundations that was used by the NASA team at JPL for their Mars rover to use assertions. The next, sequentially moving on, I've had the pleasure of working with Dr. Andrea Zeller. And 2 of the pieces of work I'd like to highlight are the first being mining metrics to predict component failures. This was on the use of relative complexity metrics to actually build cross-project defect prediction models. This was to identify whether we are able to build models from one component and transfer it to another. And the second was a wide-scale deployment of 200,000 Windows machines that were actually reporting telemetry back to see what are extrinsic factors that actually affect reliability. So this gave us the opportunity to analyze the ecosystem and its influence and implications on overall software quality. Work with Dr. Prem Devanbu on whether distributed development actually affects quality. So we see a lot of articles on either side of the spectrum, those who are actually in support or against distributed development. But there's been no studies done so far prior to this which looked at the quality perspective. So we were able to actually analyze a large several thousand-person team that was building Windows in a distributed fashion to see whether it actually was affecting quality. And we actually found out that there were actually no implications on quality. In fact, there was no difference between teams that were distributed and co-located in terms of the overall post-release failures, which is basically customer failures that is actually seen. The next is actually leveraging this to build socio-technical networks. That is using developer networks and dependencies between code structures to build an integrated graph to find out where failures occur. This is to actually go towards reorganizing teams. So as much as we actually want to look at the actual code base, the teams that build these systems are equally important. So we use these 2 to actually leverage towards the third study, which is examining the effects of code ownership, which kind of substantiate the importance for having clear code ownership for large systems. Then work with Dr. Vic Basili. This was one of the pieces of work I'm extremely proud of. This was actually looking at Conway's law. So Conway's law has actually never been empirically quantified. It's been accepted, a lot of industry people believe it, but it was good for it to be validated. So we looked at Conway's law from a historical perspective, spanning several years of Windows development. And we actually found strong influence that actually backs up Conway's law, which goes on to say that, organizational structures and code structures have to match each other for it to have perfect reliability. With Dr. Harald Gall, we actually followed up on cross-project defect prediction, which has now become a fairly large field with hundreds of papers written on it. This was one of the earlier papers that explored various ways to build cross-project defect prediction models. And the next one was actually software engineering for machine learning. I will talk about this in a little bit detail in the future slides, but the whole goal of this is software engineers actually are the people who are implementing AI and machine learning models. While AI and ML experts know the models, it's frontline engineers who have the job of engineering the system. So what are problems they face? How do you debug machine learning models? How do you debug deep learning models? When do we know whether the model is wrong or if there's data drift? How do we actually build a system that has an early warning indicator when the data drift or a model drift occurs? So some of these are touched upon in those studies. And with Miriam Kim, we had the ability to, we wanted to explore the ability to look at refactoring. Refactoring has always been thought of as a sound engineering practice. We wanted to take a step back and see whether we are able to quantify the benefits of refactoring and what are the challenges facing teams that do refactoring. So this was one of the earlier studies to actually look at the cost-benefit trade-offs of doing refactoring and the quantifiable benefits of it. With Dr. Emerson Murphy-Hill, we actually looked at a slightly different tangent. Software systems are actually not just traditional. A lot of software systems are video games or games that are played on consoles. So we actually analyzed the code for Xbox and other games to actually find out how different are they compared to traditional software development teams, and what are the differences and the positive aspects one can learn from each other. And these quantify the differences. With Dr. David Lowe, the goal was to actually understand how practitioners perceive the relevance of software engineering research. This was probably one of the very few meta-analysis papers we did. So we took several years of ICSE and FSC proceedings, summarized the papers into 2 or 3 paragraphs, and we actually sent it to several thousand engineers to ask engineers to rank which of these ideas they thought was relevant to them and which of these ideas they thought was practically applicable, so as to understand what are the top needs for engineers and what in the research community, what studies in the research community currently address those needs. And finally, with Dr. Audris Marcus, one of the studies we actually looked at was to kind of quantify the impact of coverage on code quality. There have been lots of studies which have looked at coverage prioritization, increasing coverage, automatic unit testing, etc. But this was a step back looking at system testing. So when teams actually measure overall system coverage, what is the influence of system coverage on field failures? So as trying to address the question of when do we stop testing? Because there's a finite amount of time to release a software system, and when can we actually identify what the trade-off point is for us to not increase coverage anymore. So this was a very high-level, quick overview of some of the work that's been done before. And I want to actually spend a little bit more time on looking at the future in this area. So first of all, I want to give a shout out to my wonderful colleagues in MSR as part of the software analysis and intelligence team, Chris Bird, Dene Ford, and Tom Zimmerman. Without them, none of this work would have been possible. I've been extremely lucky to have such wonderful colleagues. A lot of our focus actually sits on the 3 Ps, that is people, product, and process. So we try to leverage these 3, looking at developer productivity and overall system quality and reliability. We have 2 broad focus areas that we try to target in the coming years. One of it is on developer communities. That is, how do we foster empathy in developer communities, understanding the non-traditional software engineer experience, how do communities in GitHub and Visual Studio work? The other being future of software creation, that is software 2.0, productivity of software teams, and more relevant in recent times is how do teams effectively do remote work? And So the common goal for most of our work here is understanding productivity and build interventions to better support programmers. So towards this end, let me actually just focus on two topics in both the developer communities and the future of software creation. I'll keep it at a very high level just to talk about the results, and the details are in published papers that are linked off my website. So I'll talk about PR acceptance bias and gender diversity in GitHub projects for the developer communities, and effort estimation at the PR level, and software engineering for machine learning for the future of software creation. So for developer communities, one of the things that's very curious in GitHub is to understand the influence of geographical location on pull request acceptance decisions in GitHub. So when people actually fork, they make changes and they try to integrate back, what is the likelihood that it'll get accepted based on the geographical location of the author? So we actually use the geographical locations of submitters and the same geographical location of submitters and integrators to identify this question. We use the GHTorrent data, thanks to Georgios for doing such fantastic work for the broader community. We use around 1,000 odd projects to make sure it's non-trivial. And it represents around 1% of the projects developed using pull requests as the mode of collaboration. We use Bogdan Vasilescu's the country name manager code and others from UC Davis to actually identify which countries authors and submitters are from. And our high-level observations after controlling for project characteristics, developer characteristics, and pull request characteristics are that geographical locations actually explain significant differences in pull request acceptance decisions. More specifically, keeping a baseline, keeping the United States as a baseline, submitters from the UK, Canada, Japan, Netherlands, and Switzerland have a higher chance of getting their pull requests accepted. However, submitters from Germany, Brazil, China, and Italy have lower chances of getting their pull requests accepted compared to the US when we take the submitter and the integrator's geographical locations into account. More so, submitters and integrators having the same nationality increases the chance of pull request acceptance decisions by 19% compared to when submitters and integrators are from different countries. And on surveying submitters, we found out that submitters actually from some countries perceive to experience bias, and these observations are in agreement with the quantitative analysis. And for integrators, 53% more integrators perceive that they encourage submitters from their own nationality to participate. And 8 out of 10 integrators feel that it is easy to work with submitters from the same nationality. So a lot of this goes towards the existence of a subtle bias. The first point towards any kind of analysis is to identify and understand this so that we can quantify and improve upon it going forward. So we hope to actually set the baseline. Leading towards the next question is our work on gender diversity in GitHub. This is a large collaboration with Microsoft Research, SMU in Singapore, Delft in the Netherlands, and IIIT in Delhi. So to the best of our knowledge, this is actually the first empirical quantification we know of geography and gender diversity. When we actually look at these numbers, the goal is to actually first form a baseline. And from here, we work towards other questions, which is there is actually no strong correlation between gender and geographical diversity. And since we also track it across time and see that since 2014, there has been a small and statistically significant improvement of gender diversity in North America and Southeast Asia, but negligible change otherwise. And many of the barriers and motivations for contributing converge across geographical regions, which is the lack of resources, the goal alignment shift with their current day-to-day jobs. The poor engineering environment is a significant factor for being a barrier for people contributing, poor working environments, unclear onboarding, and inactivity on projects. So we are working towards how do we actually address several of these questions, both through qualitative and quantitative interventions. So moving to the second phase, just on the future of software creation. I mean, software engineering for machine learning actually applies across the board these days, spanning the spectrum from human resources, legal, office, research, security, operating systems for customers, devices, etc. And there are widespread algorithms that are actually used, which actually go into search ranking, recommendations, predictions, decision optimization, NLP, etc. But most of this work is actually done by frontline software engineers who actually are not experts in machine learning or deep learning. So when we actually identify the various tasks in the machine learning workflow, ranging from defining model requirements to model deployment and monitoring, we actually find out that overall the average reported hours per week spent on each of these phases remains roughly equal, with a few of these actually being smaller. And most of the respondents actually work on this activity at a fairly equal pace. So one of the problems we actually found out was that there was a lot of end-to-end tool fragmentation. There are different tools that apply in different phases, causing people to switch frequently between tools. Data collection and cleaning is hard and is usually not accounted for as much as it should be in terms of time, education, and lack of expertise. And one of the biggest problems was debugging is hard, because most machine learning models or deep learning models, when deployed, will give an output. It's not known whether there was actually there was an error in implementation. So how do we debug models is a common question that's always come up. Model evaluation and monitoring was another challenge. We also see that these challenges actually differ by experience. To some degree, things that are common to everyone are end-to-end tool fragmentation, data collection, cleaning, and management. Whereas the people with low experience actually have education and training as problems, whereas people with higher experience have scalability, model evolution, evaluation, and deployment. More from a software engineering perspective, we face challenges because we have typically actually been used to actually looking at data as different from source code. And some of the best practices we've actually learned is ML tools need to be better stitched into the ML workflow, and the workflow needs to be more automated. Centered development around data, that is sharing, provenance, versioning. There are also privacy issues with respect to data. That is, data can be retained only for a short period of time. So models cannot be retrained once the data is gone. So how do we actually make data agnostic models that can actually be retained over time? Educating non-specialists in machine learning. Machine learning models are very hard to debug. Using simple, explainable, and composable models actually help. And carefully designed test sets, scorecards for evaluating combo flights, and human in the loop to test the evaluation are all factors that have actually been significant best practices in deploying software engineering for machine learning. And one of the bigger problems that has always come up is traditional software engineering typically focuses on code and not on data. So challenges we have is how is data stored, versioned, tracked in repositories, and compliance requirements. So teams pay a lot of, teams suggest that, they pay a lot of attention to data, and typically it is difficult to know whether the data is wrong in terms of collection. So how do we actually have data monitoring pipelines which actually check for the consistency of the data? So a fair amount of work is needed in the data part of software engineering in terms of not only just storage and versioning, but also in terms of accuracy and reliability. Towards that end, though this is a current problem that's facing the community, I wanted to take a step and go back into a classic problem we've talked about, which is effort estimation. Barry Boehm has actually worked on effort estimation for several decades and has produced fantastic models like COCOMO and Qualcomm. But with recent trends in cloud development, there is actually a need for, with the pull request mechanism and online versioning, there is actually a need for effort estimation at a more local level. So for this community, I actually don't need to talk about the importance or the problems with the software effort estimation and its uses. But more so, we actually wanted to build a effort estimation model that can be deployed at the level of pull requests for each individual. So we actually built a model using several data points that are available based on telemetry, which take into account things like the number of active PRs, pull requests an engineer has, whether it's a bug fix, whether it's a feature, how many reviewers are associated with it, the age of the developer in a particular team, in a current repo, how long they've been at an organization, classic code churn metrics, temporal metrics, and also architectural metrics. We actually find out that the positive metrics, meaning the metrics that actually cause an increase in pull request time, are day of the week. This actually is in line to Andreas Zeller's work on Don't Program on Fridays. We see the same. When pull requests are created on Fridays, they take longer to complete. And of course, the average age of pull requests of a developer talking about the kind of work a person does, whether it's a bug fix or it's a complex feature, and the average age of pull requests which touch similar paths to talk about architectural complexity. Factors that actually cause a pull request to be finished earlier are the experience of the developer in the current repo and the current team, and whether they are bug fixes, because typically bug fixes actually finish faster. This is actually deployed to several thousand developers. This is just a screenshot of how it looks. This is some of our recent work. And we actually find out that overall, when pull requests are actually nudged by our system based on the effort estimates, they are actually moving 44% faster. That is, almost 50% of pull requests are completed within 2 days of us actually telling or notifying the user that they have exceeded the estimated time based on a machine learning system. So the system is called Nudge, which is actually intended to nudge the developers towards moving their pull request towards completion. An accidental result we've actually seen is it's also causing a lot of pull requests to be abandoned. When we nudge, people are like, okay, this pull request was just lying open. We are going to close it, or we are going to abandon the pull request. So that also leads to code base hygiene. And with any kind of evaluation, having a qualitative evaluation also greatly helps. So when we actually have qualitative feedback based on each individual recommendation, we actually see that 73% of the comments made by our tool are positively resolved. So the classic software engineering problems are can still be revisited in the new era with new challenges and new data coming about. And now I wanted to take a couple of minutes in the end to talk about something that as a community we should acknowledge. So I just pulled this quote out from Isaac Newton, which says, "If I've seen further, it is by standing on the shoulders of giants." And to some degree, I want to actually give credit to a lot of people who have actually been influential in this regard. And I wanted to set this up. These are a lot of people I have actually never co-authored papers with. These are people I've actually not worked with directly, but I still want to actually call out, Rob DeLine for probably his expressive writing, his fantastic managerial support, his clear thinking, and his ability to explain things very clearly. There was once a joke where people said, Rob DeLine can actually explain machine learning to Mickey Mouse. So I want to thank Rob for all he's done for the broader community, Gail Murphy for her outstanding research ideas, her leadership, her ability to think of so many solutions to a technical problem, and while prioritizing the engineering solution. And despite having won so many awards, her humbleness is actually something I always look up to. I actually had a chance to meet Mary Shaw at ICSE in 2003 when she presented her paper on how to write a good software engineering research paper. That has actually been hugely influential in making me think about how I actually write my research studies and how I plan things and how I want to quantify impact compared to the state of the art. Nino Medvedovic. Nino has actually been extremely influential because sometimes it's actually the little things that matter. I wanted to just briefly touch on a story from the ICSE PC. There was a PC meeting where I wanted to say something, but I actually kept quiet because maybe I thought it wasn't my place. Nino actually was able to identify that I was feeling uncomfortable. He called out and asked me for my opinion. By basically asking for my opinion and for my voice to be heard, Nino was being inclusive. This was almost 12 years ago. And I greatly appreciate Nino. I appreciate Nino for that, because being inclusive is something we all have to look forward to. And it is something important for us to do. Amy Coe for her courage and for her leadership. I've known Amy for a long time as an intern, but I also want to call out Amy's leadership in this area. If you actually haven't read Amy's recent Medium post on undergraduate education, I think the article is actually titled, "Our Undergraduate Program is Racist." You should actually take a look at it. It takes a lot of courage to write a post like that. Lionel Briand. Lionel has actually been, he's kept the community on its toes. We need people like Lionel to actually help us focus on industry impact, relevance, and he's probably been one of the few people who's worked the most with industry. So thank you, Lionel, for all that you do for the community. Wolfram, for actually being an excellent mentor who's put things in perspective, who's actually talked about the bigger picture and focusing on longer term goals. Jim Herbsleb for doing fantastic research on socio-technical networks, setting the standard for a lot of people to follow. And his work on open source software systems, effort estimation, and practice have actually been research ideas to aspire to. Lori Clark for her generosity in giving me the opportunity to serve on 2 National Academy of Science committees. Aside of the tremendous honor, I think my thinking on software engineering has been greatly influenced by this opportunity to serve on these committees. Jim Laris for actually always being willing to take risks, even though he was not in software engineering. He was more of a programming languages person. He always appreciated SC research, empirical software engineering, because impact was something that was to be recognized. And lastly, I want to recognize 2 people, Sriram and Pankaj, both who actually left significantly lucrative and impactful research positions in the US to take up positions in India, to actually make sure that they are reaching out to underrepresented communities in India and disadvantaged communities. Their work has, it would be great if ICSE would recognize more of such underrepresented research work, that is minority communities or disadvantaged communities in India and their access to computing. And lastly, I'd like to thank Tim Menzies for his amazing, sometimes hilarious ideas, Walter Tichy for talking about the impact of looking at things from a lifetime perspective, Ahmed Hassan for being my partner in crime and also keeping me on my toes about the kind of research projects I work on, Michael Liu for actually showing that you can have diverse research interests and still be successful in all of them, and Gerard Holzman for his generosity and humbleness that you can actually take ideas from elsewhere, apply it in the Mars rover, and the ability to acknowledge those. With that, I actually want to come up with a last statement. I just wanted to say, none of this work would have been possible on my own without an outstanding set of collaborators at Microsoft, an amazing set of interns. I only have pictures of 12. I think I had 22 interns over my time, most of whom are actually in academia now, ranging from Delft to Columbia to Brown, CMU, and York in Canada. And last but not least, I just wanted to thank the broader community. As a community, sometimes we can be very self-critical. I've published occasionally in SIGCOMM, Chi, and other SIGs, but I just want to say this has probably been the friendliest and the nicest community. Let me just close by saying it takes a village to raise a child, but I've been very fortunate to actually have SIGSOFT and ICSE as my village. I sincerely hope we can support and encourage each other, especially in these times. And to finally close out, thank you again for giving me this tremendous opportunity and honor. I don't know how to thank you for this. Thank you.
Thank you, Nachi. Well, we have quite a few questions. I assume you can hear me.
Yep. Yeah.
Okay. So we don't have time for all of them, but let me look at the popular ones. Here's the one. As a researcher in industry, to what extent do you see the software engineering research community's research on OSS, open source systems, applying directly to broader industrial projects?
So, very interesting question. This is actually very relevant because let me actually answer this as an industry researcher and not as a Microsoft researcher. As even someone outside, like the amount of work that's been happening on GitHub has significant implications for developer productivity, not only in Microsoft, but elsewhere, because whether we like it or not, COVID has forced all of us to work remotely. GitHub and other open source software systems were actually always working remotely. There is a ton we can learn from these systems that can be applied to industrial practice. So the relevance is absolutely there. In fact, it's industry that's catching up with open source software systems on how to work remotely. So there's a lot to learn, not only from remote work, but how to manage builds, how to actually manage asynchronous communications. These are things that the broader community can learn from OSS research.
Okay, great. Here's a good one. As a student, I'd like to know more about how you find the problems you work on. You seem to have found many interesting ones.
So very good question. So usually the way I find problems is I always end up talking to people and finding out what actually bothers them a lot. What bothers them a lot? Is it something that's scalable? Is it something that's worth addressing? And typically I've tried to pick problems that have a research flavor and an engineering flavor to it, because sometimes a lot of the problems can be an engineering fix. So those are the kind of problems that are better solved by engineers better than me. Whereas problems that have a research component, those are the ones that actually excite me. So I typically try to find these by just talking to people, and the community is a fantastic community to talk to. And as a student, I would strongly, I mean, this year it's unfortunate, but there are actually virtual lobbies, rooms for you to hang out. You should feel free to email people. But as a community in ICSI, I've got a lot of ideas just by talking with people, brainstorming with folks. So that's a great place to start.
Good. I think we've got time for one more. What do you see as the next big thing in empirical software engineering or beyond empirical software engineering?
So the next big thing, I would actually look at it in two prongs. One is from the people perspective, which is how do we actually make remote work succeed? Because the reality is people are across time zones. How can we actually have tools that make asynchronous communication as less disruptive as possible? And the other aspect is from a technology perspective. Machine learning and AI is here to stay. How can we actually build a better debugging and tool support for machine learning models? Because machine learning models will no doubt give an output whatever happens. How do we know if the output is correct? How can we build verification tools that check the output? So those are two prongs that I actually think will be very important in the coming years.
Very good. I think we're about, we need to move on to the next talk. There's still 8 more questions. So, after this session, hopefully you can go out and find a hallway. I know there's a specific way you can do this. Hopefully you can go out and find a hallway, and people who have these other questions can meet up with you.
Absolutely. Okay. Thank you very much again.
Thank you. Yep.
Thank you, Nachi. Thank you, Greg. And Nachi, congrats again for the award. Great job. So now we move to the final presentation. So this is the presentation for the ACM SIGSOFT Outstanding Research Award. And this award will be presented by Tom Zimmerman, who's the SIGSOFT chair.
So it's my pleasure to present the ACM SIGSOFT Outstanding Researcher Award. I want to just say a few words about what the award is about. The award basically recognizes outstanding individuals who have made significant and lasting contributions to the theory and practice of software engineering. It's similar to the Harlan Mills Award. It's one of the highest contributions that you can achieve for software engineering research. And this year, the committee was chaired by Gail Murphy, and committee members of the selection committee were Mark Harmon, who won the award last year, Sebastian Uchitel, and Anita Sama. And as recipient of the award was Michael Ernst selected. And I want to just give a few examples of Mike's impact and achievements over the past years, because he has a very impressive record. So first, he's very well known for his DICAN work on detecting dynamic invariance, which has had a lot of influence on the research community. It enabled the extraction of models and specifications from real-world software. It allowed with the detection of unwanted side effects and change effects, and it also supported program understanding. Mike is also known for his run-loop work on automated test generation, which is among the most widely used approaches for test generation at the unit level. And he's also very famous for his checker framework, which added pluggable type systems to the Java language and also prevented many mistakes being made in software. And with this, I want to congratulate Mike for this outstanding award. The award citation is for contributions to programmer productivity through software analysis, testing, and verification. And I look forward to your presentation.
Thanks. Can you hear me and see my screen? Fantastic. So thanks very much for that introduction, Tom. I really appreciate it. And thank you to the community for giving me this award. I'm always in awe of the great research that's being done by a lot of people. Some of them I think may be more deserving than I, but I appreciate you recognizing me. I was trying to think about how to title this talk. And traditionally what people will do is do a deep dive into one particular research result that they have achieved. And I was feeling very uneasy about that. I mean, it's sort of like asking a parent who's their favorite child. So if you only have one child, that's an easy answer. And otherwise, it's an impossible thing to answer. So I'm going to give a very high level, quick overview of some research, in particular what Tom just mentioned. And then I'm going to talk a little bit more about my approach to research and what led me to make these, to get these results, and how you might use it too. So I thought of titling this this talk. Sorry, I'm having a little trouble with the screen sharing. How to be a better researcher. But I thought that was a little bit presumptuous. So I'm going to instead call it How to Be a Better Researcher Than I Am. These are lessons that I've learned from a career of making mistakes. I'm hoping that maybe you won't make quite as many. So I think the biggest question is, what should you work on? Choosing great problems will make you a great researcher. And if you ask me that question, I'll give you an answer. And that's it. I have no idea. You're the only person who can really answer this question. But what I can tell you is where my ideas have come from. And my ideas have primarily come from two places. The first one is my own inadequacies as a programmer. I make a lot of mistakes, and I get angry when I make those mistakes. And I want to not make those mistakes anymore, and I want no one else to make them either. So then I'll go off and spend 5 years, and then no one will make that mistake anymore. And in the meanwhile, I've made a lot more mistakes and generated a lot more research ideas. The other place my ideas come from, and this is really the majority of them, is from my colleagues who are full of ideas, many more than I could have. So I'm going to give some examples. These are my 3 greatest hits or my success disasters. They're exactly the same ones that Tom mentioned. They're the ones that I'm best known for. I mean, oftentimes people will ask me about these when I'm at a conference, and it's kind of like when you're in a cover band and someone asks you to play Freebird again. I mean, it's a good song, but do we really need to hear that one? Can't we hear something that something a little more recent? But nonetheless, I think talking about the source of these ideas might be interesting. So I'll talk about specification inference and test generation and formal verification. So the specification inference is it's a tool called DICON. The input is program executions, and the output is a likely specification of the program. The way it works is through machine learning. It essentially generalizes from all the observed values. And there's a little bit more to it, but it's not that important for this particular talk. Some examples are things like x is greater than the absolute value of y, or for every node n, n equals n.child.parent. Things like that. So where did this idea come from? It really came from my frustration as a programmer. I had a lot of trouble programming. And I felt like almost all my problems came down to one issue, which was that the code was not documented. And this included my own code that was written 2 weeks ago. I got really mad because when trying to think about what difficulties I was having, I always ended up concluding, well, if only this code had been documented, everything would have been easy about it. I would have understood it. I would have been able to deal with it. And without the documentation, I wasn't sure how to make changes. I wasn't sure what the impact of those changes might be. So then I thought, well, there are a lot of problems I could solve as a researcher, but wouldn't generating documentation be something even more valuable? It seems to subsume it. Another way that I came about it was by thinking about, was from a more theoretical point of view. So I had noticed that the strong duality between static analysis and dynamic analysis. I hold that for any problem you can solve using one technique, you can solve that problem using the other technique. If there's a static analysis, you can make it into a dynamic analysis. If there's a dynamic analysis, you can turn it into a static analysis. So I made a really long list of problems and analyses, everything that I saw anyone in the literature looking at. And then I looked for missing entries. I looked for places where there was a dynamic analysis, but not a static one, or there was a static analysis, but not a dynamic one. So for instance, I'm very interested in specification and verification. So validating specifications, to do that statically, you usually use some kind of strong theorem proving approach. Dynamically, you just run the assert statement. So what about creating specifications though? Usually people write them down, human beings do, but they can be generated automatically via some kind of abstract interpretation or another static analysis. But what would the dynamic analysis that is the dual to that abstract interpretation be? There was a hole there, and I wondered if we could produce something. So that's where the idea for DICON came from. For test generation, there's this Randup tool. It takes as input a program and produces as output some unit tests, both regression tests that will help you find defects you introduce in the future, and also error revealing tests that indicate defects that are already present. And the technique is to randomly generate tests, heuristically classify them, and then use that classification as feedback into the random exploration approach. So an example is this test you see here, where the first 5 lines are the test setup, and the last line is the test oracle. And this particular one was generated by Randup, and it indicates a bug in the JDK, where the equals method does not return true. So where did the idea for Randup come from? Well, primarily from my frustration as a programmer. I know that testing is really important, but like most programmers, I don't really love writing tests. It's not the sort of thing that I want to do, even though I know I ought to be doing it. So I wished I didn't have to do it. Another motivation, perhaps a less pure one, was that when reading the literature, I felt like there were some mistakes being made that needed to be corrected. One thing that I saw a lot was people who would do comparisons to random testing. They would do some kind of test generation approach, and they were actually doing a good evaluation in that they were evaluating, comparing to another technique. An evaluation shouldn't just run your technique, it should run multiple techniques and show your technique is better. So they were comparing to random testing, that was good. But the random testing that they were comparing to wasn't very good. Essentially, they would implement the simplest possible thing and say, we're better than that. Here's an example of some code that people would say is a reason you shouldn't do random testing. So this particular routine, they would say, there's only 1 in 2 to the 64 chance that any test would find this problem. But suppose you're a programmer and you see this. How would you test this? Well, you would probably use the constant that's in the source code. And there's no reason a random tool shouldn't do that too. I think what I wanted to see was I wanted to see people comparing techniques, not tools. If you're comparing your particular generation technique to random, then you should implement all the same ideas and techniques in both. Another problem with previous work was that it mostly generated illegal tests. It would pass null to a routine, the routine would crash, and they would say, we found a bug. But in fact, that routine was not supposed to receive null. I'll talk about this third project, this formal verification project. The input is a program plus extra type qualifiers you write on the type. And the output is a proof of correctness or an indication of a defect. And the technique is just type checking. So here's an example. You could have a send routine that sends a message over the network, and its type is specified as encrypted string. So now, if you pass an encrypted string, like the first call to send, that's okay. If you try to pass a plain old string, then that's a compile time error. So this has been used in dozens of different domains to prevent various errors like this. So where did I come up with this idea? Well, it's because I was having a lot of trouble as a programmer. I worked on a 1,000,000-line Lisp program. I worked on a 100,000-line Perl program. The first version of DICON was written in Python, and it would run for 8 hours, and then trying to produce output, it would crash because I'd misspelled a variable name. I didn't want this to happen. So, and I thought a big part of the problem was the lack of type checking. But really, it's not just type checking errors. Any error should be preventable at compile time. Another reason is that I felt like a verification tool should be both sound and useful. And I felt like half of that was missing from previous work. Some was very theoretical, but it would be 5 papers before they admitted that it didn't work for the visitor pattern. Others was hacky and found some bugs in practice, but it didn't give you any guarantees. And so I wanted to make it easy to write that. So I started working on type systems, and I wrote a compiler every year for 8 years. This got really old, and I decided maybe I should build a tool to make this easy to write. So I built a tool that makes it easy to write new type systems. Another theoretical motivation is that I really love the idea of verification. I think it's a fantastic, nifty idea. And I just wish it got used. And especially then, it just didn't get used very much. And I was trying to figure out why and what we could do to understand that and to improve it. Now, the notion of using type qualifiers was not a novel idea, but no one knew whether it was a good idea. No one had done any evaluation in practice. There are previous papers that talked about this, but they hadn't really implemented it and evaluated it in practice more than for one table in one paper. And once we did, we found lots of new research questions. It was much more than a matter of engineering. If someone says something is just a matter of engineering, that usually means they're not an engineer. So thinking about these particular projects, it's interesting that Daikon and Randup have been the most, had the most impact in an academic sense. I think the reason is that they can run push button as a subsystem, and they produce an artifact. For instance, now, if you have a research technique that requires a specification, you can run on any program you want, because Daikon will produce a specification. It's weak, it's partial, it's not guaranteed to be correct, but it's a lot better than nothing. And the same for testing. If you have a technique that requires a test suite, now every program has one generated by Randup. Again, maybe not complete or perfect, but good enough for you to evaluate your technique. On the other hand, the checker framework's been much more industrially successful. And I feel like it's generated a little bit less excitement in the academic community. And I think a reason there is that it requires effort for every code base to verify real bugs. It requires you to write annotations. And that might help make people's code more correct, but it doesn't help academics publish a paper. Now, as I say, we've had many other projects. Most of my projects failed, but others we declared victory after a few papers. I think in some cases our problem choice wasn't great. In some cases we didn't follow through enough. In others we're still waiting to see the impact. And sometimes there are other reasons. I said the one source of ideas is my own frustrations, and the other is my collaborators. I've been very fortunate to work with an extraordinarily talented group of people without whom I could never have done this work. Here are 234 people I've published papers with. I've also done research with about 100 more undergraduates that didn't yield a published research paper in a major conference, but nonetheless helped them to get better jobs. These are people who've helped me to learn and whom I've had the pleasure and honor of helping to learn. Working with other people is tremendous fun. I'd like to talk now in the second half of this talk about my approach to research. And I'm going to talk a little about pursuing ideas versus results, about working on things you love, about making your work available to others, about not giving up, about critiquing other people's work, and about things that I think the community should do. Now, these are things that have helped me, and I've had some measure of success, but you will never have success trying to mimic someone else. But what I do encourage you to do is to think about these and whether they can think about how you've already done them very successfully or whether they can help you in the future, especially younger members of our community. So first I want to talk about the difference between ideas and results. An idea is a thought or it's a suggestion. A result is evidence that answers a question or provides information. And I always try, I don't know if I always succeed, but I always try to pursue research that yields results, because I think that's the best research. When you think about ideas, most ideas are terrible ideas, and that includes my ideas. And most ideas are not novel, and that includes my ideas. Let me give a little evidence for each of those 2 points. In terms of ideas being terrible, there is, even in the popular press, like in the New York Times or elsewhere, there's an increasing recognition that the scientific community is having a lot of trouble with reproducibility. There's a famous paper down below, Why Most Published Research Findings Are False, and it gives 7 reasons that I've listed over here on the left. Bias, too much independent testing by independent teams, any one of which gets to publish, studies being too small or effect sizes being too small, or too many relationships being tested so that one of them is going to be accidentally true, vague or flexible definitions, and financial interests. I don't think this is malfeasance usually, but when people are so eager for results that they take the first thing that looks like one and publish it, then we may not be helping science. In terms of most ideas are not novel, there's lots of examples of important concepts that were discovered simultaneously by multiple teams. So the calculus, oxygen, evolution are examples, many others, but here I've also listed a few examples in computer science of things that were generated completely independently by different people. I also know this because a bunch of times I've been scooped by other people, including some of you on this call, and other times I've scooped some of you, and I'm sorry about that, but I was just lucky in terms of the timing. So I think in our community, we need more results. There are some arguments in favor of ideas. So ideas can be an imaginative contribution. They show connections between areas. They spark even more ideas. It proposes work that other people can do, and it's a good thing to put on your CV. But I think results are better because most ideas are of no value. It's actually pretty easy to make up a persuasive argument why some idea is a good idea. I'll give you an example later on. Sometimes if people only want to publish an idea, I wonder, why aren't they willing to do the work to produce results? Maybe it's because they don't really believe in their idea. Oftentimes when people have an idea, they're permitted to have a much less extensive evaluation, and those evaluations can be very misleading. Also, subsequent publications become very difficult because people will say, oh, you didn't have the idea, even if they had it, or even if they're doing better evaluation. I think work should be actionable. When you publish a paper, I think the whole purpose of publishing a paper is to change the way people think and act. After reading your paper, people should behave differently than they behaved before. And so I like to ask that question. And I think if so, then you're making a contribution as opposed to just putting some more data up there. So this is not a new debate. Walter Tichy wrote an article more than 20 years ago in Computer asking, should computer scientists experiment more? And the answer was yes. We do experiment more now, but I think the answer is still yes. I was a graduate student at the time that paper was published. And I remember that there was significant debate about this. A lot of people had critiques. They said, if you require people to have experiments in their papers, you're going to slow down the dissemination of ideas. You're going to slow down scientific progress. You're going to waste resources doing these experiments that aren't necessary. So when I tried to parse and understand what they're really saying, they seem to be saying, my ideas are uniquely valuable and should be disseminated, even without evidence. My ideas are obviously good and don't require an evaluation. And I don't really like to do that work anyway. I think I shouldn't have to do it, or someone else should be required to do it. But again, if you believe in your idea, I think you should believe in it enough to do the work. I think publishing some ideas is a good idea. Some of them are good, some of them are novel. I think it's really good to explore a design space, to justify choices and draw these connections. We should recognize the limitations of something that's just an idea. And we should recognize that different results are valuable. But there's a danger in publishing too many ideas or only ideas. It might be good for the count on your CV, but it's bad for science because a trivial evaluation or contrived evaluation is actually much worse than no evaluation. Because an incorrect evaluation can cause us to expend resources and time on topics that, on dead ends. So I think if you believe in an idea, you should evaluate it, you should implement it. You shouldn't expect to get scientific credit for science fiction. You should be able to convince people so that you can get it published. So a second topic in my list of my research personality is to scratch your own itch. Think about problems that you care about. I think it's actually really important to use your own tools, your own techniques. This is sometimes called dog fooding. If you're not willing to use it, then do you even believe in this? If you're not willing to use it, do you even understand the domain? Do you have a deep understanding of what people need, what the true problems are? If you're just an outsider and not a user, you probably don't understand that. I also think you shouldn't pursue fads. Now, I've missed out on some research in JavaScript or in mobile development or in quantum computing because that's not the kind of programming that I do. But there's plenty of work, and my general work is applicable enough to those domains. I'm also not a fan of using the related work section in a paper, the future work section in a paper to suggest a project. I'm not positive those are always good ideas. I think the literature is great to understand existing techniques and it's good for inspiring new ideas. But I think coming up with your own approach is a way to have more impact and to incrementally build on someone else. I also think you should choose problems that are grounded in practice. Whenever you're writing a paper, you should be asking, why does the reader care? How is the reader going to change their behavior after this? And if you can't answer that, maybe your research isn't done yet. A corollary of this is that I think it's really important to be a programmer if you're working in software engineering, or at least in the part of software engineering that works on programs. It generates a ton of good ideas from your programming. It ensures your work is relevant. It leads to impact because people can use your work. And it's a lot of fun. This is more fun than like grading exams and writing grant proposals. So implementation enables you to evaluate. I think evaluation is essential for understanding a technique. It's essential for evaluating it and for determining whether it's useful. And every time I've ever done an evaluation, I've always had surprises. The difference between theory and practice is much larger in practice than it is in theory. And just a ton to learn. It also helps the field because other people can build on it and other people can be inspired to do better. It enables these comparisons, and comparisons are at the heart of science. So relatedly, I think we should publish our implementations. It lets other people work faster. It increases the confidence in your work. That increases citations and impacts. And I think the community should prioritize this. I think artifact evaluation committees are a good start, but I think we have further to go. I also think it's important afterward to maintain your artifacts. I've actually, for most of the papers that I've published, done more work after than before, at least for these success disaster projects where people continue to use them. I still get bug reports every week on the tools that we talked about today. So maintaining the artifacts means other people can compare it and build on it. It means other people can disparage the work, they could scoop you, and it distracts you from other research, but I still think it's worthwhile. It's essential for scientific progress. And this is really badly rewarded by the scientific community. People are always wanting to pursue the shiny new thing, or valuing novelty over effectiveness, or valuing the number of papers over their scientific value and their impact. And this is a thing that I think the community can do better. So reproducibility is absolutely essential for scientific progress. So I think you should make all your work publicly available, the tool, the evaluation scripts and inputs, the outputs. This is extra effort, but I think you should make it easy to use beyond just the experiments in the paper. So some people choose not to do this, and there are reasons for that, but I think those people aren't really fully acting like scientists, and they should be, we should recognize that and reward them accordingly. I think another thing that's really important, moving on to a new topic, is to believe in yourself. So you should work on ideas you believe in, and you should believe in yourself. Most of my papers were rejected before they were accepted, and they became better as a result. A paper rejection is a gift. the reviewers, though sometimes they're a little bit mistaken, it's always valuable to get that perspective and to understand what I did wrong to help to make them misunderstand. Also, don't give up after the paper's accepted. It takes a lot of time to turn ideas into results. Impact comes from follow through. It also takes, so as I mentioned, I've made hundreds of releases of each of the tools we mentioned over decades after they were published. And that's why they had impact, not because of the original paper. And it also takes a lot of time for opinions to change. I've had 10 best paper awards and 4 impact paper awards. And there's only 1 paper in the intersection. They were not recognized at the time for the most part. So when you're doing evaluation, I think it's really important to not show just that your tool works, but show that it's better than a well-implemented and well-used technique that tries to solve the same problem. So that may require you to fix or improve previous tools. And I think it's also important to evaluate the whole task, not just one part of it. So look at an end-to-end evaluation. So for instance, for testing, think about finding defects, not about secondary criteria like coverage or mutant kill rates. And involve the user if possible, because we're doing all this work to help programmers or to help UI designers or to help end users, whatever they're doing. So think about the most important aspects of your evaluation that needs to be realistic and make that as realistic as possible. So that's going to slow you down. But science is about truth and results. It's not about the number of publications. So I'll skip over this in the interest of time, because I only have a couple minutes left. Another thing that I've often done is to automate what people do. So I watch how programmers or users work, see what the problem is, use the insights that they would use, but then you rarely want to do it just like the people do. You want to transform how the people work. Another thing that I think is really important is keeping the work simple. I think the best papers are the ones with really simple ideas. So simple they say, oh, I could have done that. Because you know what? I didn't do that. I didn't have that idea. Someone else did. And then they were able to explain it elegantly. I think when people say this idea is too simple to be published, I think that that is really hurting our community. I also think it's a really bad idea to say something is easy or obvious. When people say it would be easy to do this, well, if it was so easy, why didn't they do it? I mean, there's a children's book in the upper right-hand corner that explains this for people who have a problem with that. Also, when people say it's conceptually easy but uninteresting engineering, why didn't they automate it if it was so easy? So there are a lot of things that are really obvious, like the Earth is flat and the sun revolves around it. The middle picture here is Spencer Pearson, a student of mine. We were reading a paper in reading group, and he did some experiments and presented the results because there weren't any in the paper, and said, let's try to understand why the technique works. So we spent a bunch of time trying to figure it out, and we finally came to an intuition, which none of us had before. It was super useful. And then he said, actually, you know, the results I just showed you were all backwards. I negated all the numbers. And, but we had convinced ourselves that we understood it. So the gentleman at the bottom is Aristotle. He said that men have higher body temperature than women. Maybe that's true because thermometers are pretty bad there. He also said men have more teeth than women. This is something he could have counted. Don't be like Aristotle, ever. Be like Spencer. So these are some of the things that I've done. I'm really looking forward to hearing about your research because I've worked in one time on some projects. I'm really looking forward to hear everyone else's too, because you know, science just keeps going forward. So I think the community should be given credit for where it's done. And I want to just once again thank my collaborators, and I'm happy to take some questions.
Thank you so much, Mark. So we have time for a few questions. So the first question is going to be, how did you decide which of your tools you should keep maintaining?
That's a great question. I mean, I call these tools success disasters. They're the tools where I'm still getting bug reports and still maintaining them. I think it came down to the ones that I was most personally involved with and the ones that the most people were using. So when I saw a lot of people using a tool, I wanted to maintain them. I wanted to support that. I think, so it's sort of half a decision you make and half a decision the community makes for you.
So the next question is, how do you envision that the software engineering, computer science research community could evolve to give a proper incentives to promote real growth, usefulness, science, and tool maintenance?
So that's a good question. I think one thing that we need to do is to appreciate the value of empirical research, of experimental research. So right now, oftentimes papers will be rejected because that idea isn't new, or that's merely an evaluation that shows some previous paper is wrong. That's new information. That's incredibly valuable. It's also really valuable to learn how a tool changes the behavior of human beings. I think that's as interesting and valuable as a new algorithm is, because our goal is to change the behavior of people, not just to publish a new algorithm. I would like to see stronger requirements on reproducibility. And I think best paper awards are great at the time. They're also really essential for young faculty to get tenure and for graduate students to get jobs. And I recognize the value of that, but I'd like to see more of an emphasis on retrospective awards. We give one award 10 years later, but I think those are actually a better measure of value than we can do at the time.
And we have one more question, which was related to your discussion of ideas versus results. Would you get rid of a new ideas track at ICSE, based on what you said?
That's interesting. So as I said, I think publishing some ideas is good, but I think we want to recognize the value of an idea. And I think if one person publishes an idea and another person publishes an evaluation of the idea, we should give the latter at least as much credit as the former. It's also the case that if you look at the near papers, they often have some kind of evaluation as well. It's like workshops. At workshops, the papers may or may not be interesting, but the discussions that come from them are fantastic. That's a really great reason to go to a workshop. And I think NEAR serves a similar role in bringing the community together. And I think that that's great.
We have one final question. Did you consider open sourcing any of your tools to increase technology transfer and possibly reduce your tool maintenance efforts?
Yes, so the tools are all open source. They're on GitHub. You're welcome to open a pull request. There are, I mean, if you even just looking at DICON or Randup or the Checker framework, they have 100 different people who've made commits to them. Maybe not quite as many for Randup, certainly that many for the other two tools. So it's also the case that people have formed companies around these tools where I had no equity, I didn't get any money from it. But again, you choose what kind of impact you want to have. One kind of impact is create a company, keep it all closely held. Sometimes people won't use something unless they can pay money for it. But another way is just put it out there and try to let whoever wants use it as they will. And that's the approach that I've taken. I respect people who've taken the other approaches too.
Okay, so thank you so much. Congratulations again. And yeah.
Thank you.
Thank you. And I think I hand back to Alex.
Yeah. Thank you, Tom. Thank you, Mike. I mean, great talk, and congratulations on the award. So this concludes the award session. I would like to congratulate again all the winners. And in closing, I just want to mention that there's additional awards, such as, for example, the ACM, the 6 of Distinguished Paper Awards, and other awards that were presented in other sessions, or they were listed elsewhere. So what we discussed are not the only awards that are recognized at ICSE. So you can find them all on the ICSE 2020 awards pages. So I encourage you all to go and check them out. And with this, many thanks again to everybody who attended the session, to all the presenters. Congrats again, and enjoy the rest of the conference.